Time online.
Can you start sharing?
This one. And is doc 1. How is it?
The voice is good. In the meantime, can you stand up so that...
Sure.
Is it okay?
Yeah, look so. Maybe you can lift that a bit more, so it's going to be like this one only. Yeah, okay, it looks good.
Is everything okay?
Yeah, everything seems to be okay.
I'll just go grab or something.
So,
I have checked it.
everything seems to be in order except that I'm unable to display my screen to you guys. Lecture. But these projectors on, so I think they're not even on. So we're good to go except that I'm unable to display my screen to you guys. Why not? So Mustafa left. Wireless. Okay, dock 1.
3 hours. I run around 3 different shoemakers. And I travel by bicycle
Not that. Wireless. So we actually supposed to go, but I cannot display. Oh, you see my presentation is over there. Can you see the presentation in that television too? No. Only this one tiny television. Okay, so what's the difference in that and others? That I don't understand, because that's supposed to be the same than others. Can you guys see if the television is on? Like maybe it's, the switch is completely off. Could that be the case? Okay, all right, so the projector, because each of the settings seems to be same, but the one television only is collaborating. Oh, okay, guys. I think it's going to be better momentarily, because this is a docking station 2. Okay, and I need to change this to be dock 2. Okay, we're good. Very, very good. All right. Third lecture. You guys good to go? Me too. Respect. Okay. Here's my plan for today's lecture. So we're gonna get started by looking a little bit of what is the deal with the finite element method. And we're looking at the basics of the finite element method. And then after 45 minutes, 50 minutes roughly, we're going to have a break. And after the break, we're going to discuss something completely different. And something completely different will be my presentation to these ERC advanced interviews. You will be representing the panel members. And then you will take a look, like how much you like it, what are the things you didn't like it so much, and then if you can provide me any feedback. Each of the feedback is worth of 1 extra point to in-class quizzes. So this could be your opportunity to collaborate and my opportunity to get some feedback. And my presentation, I started to do the presentation this morning, is not yet great. I mean, the slides-wise is not great. The stories are fantastic. Slides are not great, but I hope that we can get started. And I hope that it's okay to you that from every week this on, except next week, I'm going to do this presentation to you, like week after week after week. So we have still multiple weeks to go, because this is one of the things that is playing a major role in my career, if winning this thing. All right. Okay, so that's a plan for today's lecture. How that sounds? It's okay. Okay, very good. Okay, so let's first look what we discussed a week ago. So a week ago, we looked at how is this Rodriguez equation that is based on the concept of using two different vectors. The one that is going to be rotated and the one that is acting as an assisting vector. An assisting vector is unit in length. Assisting vector is needed because otherwise you are unable to define the rotation in a proper way. It goes like this. Here's the vector you want to rotate. You want to put this in a certain configuration in space, in three-dimensional space. So you're going to take this assisting vector. You're going to attach this assisting vector, your original vector. You're going to introduce a rotation amount of theta. And this is going to put this vector in another configuration. Now, comparing the original and final configuration, you can create the 3x3 rotation matrix that consists of a total of 4 parameters. And these 4 parameters are 3 components of this assisting vector v, and then the angle theta. And these 4 parameters cannot be selected as you want, as this assisting vector is unit in length. So this unity introduces constraint. And this constraint, in turn, gives us a situation where we actually have 3 parameters. So 3 parameters that can be freely selected, because 4 minus 1 constraint, so that's going to be 3 in total. And this is a this is a representation that is heavily used in most of the engines. Not necessarily in a pre-processing phase or post-processing phase, because 4 parameters is hard for human to deal with, for a clear reason. Because in our world, in a human world, we have 3 rotations only, and 4 parameters is going to be cumbersome to use. So it's actually possible to create the mapping from any 3-parameter representation like Euler angles to Euler parameters or these Rodriguez sequences. So the engines and the pre-processing, post-processing works a little bit differently. All right, so then we learned another method that is kind of like follow-up or extension of Rodriguez equation called Euler parameters. And this is a name game. So we're calling certain components in the Rodriguez equation by certain names. By doing so, we're going to get, again, we're going to get the 4x4 rotation matrix that consists, again, 4 parameters. And these parameters, one more time, are not able to be selected as you want because this vector v that you can see in this name game must be unit in length. So that's what we discussed a week ago. We also discussed about how is that we can make use of this technology for robot kinematics. And surprisingly, I learned earlier this week that the robot kinematics is a subject matter that you guys have learned already in the bachelor level courses. There is a course entitled as a robotics. And robotics, there is something like this kind of kinematics is, at least in certain level, is explained there. So do you guys remember that, or you still don't remember that so clearly? So it's like you have heard about it. All right. Okay, so this is, for those of you that have took this course, robotics, maybe you're familiar with this, but now what we did, we related this representation to what we learned earlier about the technology that is based on the body reference coordinate system. And simply speaking, this is nothing but reorganizing our representation. A representation that was based on translational vector R and rotational matrix A, and we're going to put them in a 4x4 rotation matrix such that upper left corner will be occupied by rotation matrix. Upper right corner will be the vector that describes the translation. And when doing so, we can take these two components, translation and rotations, simultaneously into account. Okay, as it is expressed here, we have 6 parameters. Because this guy here, this vector R, consists of 3 components. This one here consists of 3 independent parameters. So it's the 6 components. Technology that is often used here, it is called Denavit-Hartenberg, or similar, where 6 variables is no longer used, but more limited number. And more limited number, like in Denavit-Hartenberg, is going to be of 4 parameters, 4 different configurations that will be used. All right, so the beauty of the 4x4 transformation matrix is that you can create the kinematics more or less automatically, such that you can travel from one point to another, take the orientation into account, and when you keep on multiplying these 4x4 matrices together, you can travel from root to the end, and that's the way you can describe the robot kinematics. Okay, and the Denavit-Hartenberg, as explained, consists of 4 parameters. These 4 parameters, not necessarily clearly displayed in this slide, but they are the ones that take the arm length, twist, the difference in this direction, this like white direction, and the length into account. And once you do so, only thing left you to create the kinematics is
The slides are frozen on
the slides are frozen. So starting from where?
the first page.
First page. Okay, so let me take a look. Discard. It looks okay here. So let me put this back. So was it?
Now
It's okay now. Okay, so let me, okay, but I need to deattach this. Put it back. And like this. How it displays.
now I can see your cursor moves around. Your mouse, I can see it moves around.
Okay.
Here.
Can you see this? So is it moving?
No, it's still on that.
Still in this one,
Yes.
but there is a delay. How come it's not in this presentation mode? Because everything else seems to be okay. So should I, what if I do this? Is it like somehow video capture device? Everything should be okay here. As far as I can see, I don't see any difficulties here at all. No, this is what I don't want to do. Okay, so one more time. What is it you can see there? Denavit-Hartenberg. How come it's possible? Because my slide is completely different. So what is you see now? Still the same. Okay, guys, sorry about this. So it seems that we are not able to somehow change the slides and presentation in PowerPoint. So the OBS is somehow video capture device. Display, what if I'm gonna do the display capture like this? Window. Okay. How about now?
I can see OBS.
OBS? Is it?
Now it's okay.
Now it's okay.
Yep.
Okay. Okay, guys. Hey, sorry about that. So I know that is a little bit annoying that every now and then I'm facing these difficulties in YouTube streaming, but I still want to go with the YouTube because I feel that is superior. Superior in a sense that I don't know if you guys are using this, but another day I was checking my lectures, which I usually never do. But I was checking like how far I was able to discuss things a week ago. And it's so convenient that you can put this closed captioning on. Because even though that I have an accent, it's able to understand my English like almost like perfectly. And I don't know if you knew this, but you can put the closed captioning to any language you want, including Finnish. I don't know if this is what you want, but it seems to be making that pretty good. So you can put in German or any language you want, and it's still not displaying. Why?
It was good a moment ago.
It's somehow very unstable today. Huh. So it's again dark.
Yes, it's still
I think it is somehow related to this display thing that when I put it in this overhead projector, is getting confused. It seems so. So let's one more time. Let's use this one more time. All right, like this. What is how it look at the moment?
Robot kinematics.
Okay, robot kinematics. So it's exactly
Then it
what.
moves away. Now it's fine.
Now it's fine. I think it is related to this projector business somehow. Okay, but again, so what I wanted to say is that this YouTube, even though that it is sometimes a little bit of headache, and sometimes the streaming is not going smoothly, it comes with the great benefits that you can put the closed capturing and this kind of thing, and you can. I think it is quite easy to use afterwards, and you can use it. You can take a look at that in any device you want, including your mobile phone. So that's something that I myself, I'm a big advocate of YouTube. All right. So we were here. So sorry about these technical difficulties. So we were here to explain the 4x4 transformation matrix, and we concluded that you can create the kinematics based on that in a very straightforward manner. Then we discussed, this was actually a story that I was able to finish well, and I'm not going to planning to do that today either. So I'm going to revisit the subject matter a little later. We learned that we can relate angular velocity vector and time derivatives of generalized rotational parameters with help of G-matrix. G-matrix is something that is very pleasant in terms of usage of any dynamic engines. And it's kind of needed because otherwise you're supposed to express your inertia parameters, including your inertia tensor, using 4 parameters if you're, for example, using Euler parameters. And that's going to be mission impossible for human brains. And this G-matrix helps you to do that. I'm going to revisit in this subject matter just before we summarize and just before we revising or kind of summarizing our knowledge for midterm exam. Okay, but what I wanted to do today is this. Let's jump into the method that is called the floating frame of reference formulation. This is something that is a great method that is used extensively in industrial applications, is used extensively in most of the industrial companies, also in Finland. This is something that allows you to describe deformation of bodies. How it works? It works in a way that we're combining two methods. Two methods that we're going to combine are multi-body system dynamics and finite-element method. Theory goes such that if you are not happy with the finite-element method, you can combine this with something else. But in practice, it's always a finite-element method that is combined. So that's what we're going to take a look. And we're going to make a short visit to background of finite-element method, like how it actually works. Because this is something, in order to understand fully the theory, it's good to be aware of what's the method that is called the finite-element method. All right, so that's what's going to happen. This is something we discussed a little earlier. So this floating frame reference formulation is a method where there are large relative translation and rotation. The one that is described by this body reference coordinate system, that's described by using multi-body system dynamics. Sometimes this is referred as a large rigid body motion. I mean, theoretically it's not the correct term, but it's something that if it helps you to understand this, go ahead and use it. So it's a large motion that takes place. An example could be like crankshaft mechanism. If you look at the connection rod undergoes large translation and rotation. This is taken into account by using multi-body system dynamics. The deformation that is superimposed to this large motion, that will be accounted by using the finite-element method. And that's the way we can make a use of the most positive things of the two methods. Finite-element method is very good to describe relative deformation with respect to reference frame, whereas the multi-body system dynamics is very good to describe large reference motion, rigid body motion, if you may. Okay, so that's how it goes. And where this name floating is coming, this is we're gonna get this a little later. But the theory goes like this. Remember, when we look at the kinematics, we wanted to describe the kinematics using the body reference coordinate system. And the body reference coordinate system is the one that is located here. So we're gonna first take a translation of the body reference coordinate system into account with help of the good friend of us called vector R. And then we're going to take the orientation of body reference coordinate system into account by using the 3x3 rotation matrix that you can describe by using Euler angles, Euler parameters, whatever means you want. And then comes something that we have not discussed earlier. So we're going to go and describe a arbitrary particle by first taking its orientation, its location into account by using position that is related to undeformed configuration. So when there's no deformation whatsoever, that's going to be described by using U bar 0. And then comes the last component that will take a deformation of this particular point into account. And this deformation, of course, is a function of time and will be described by using the vector U bar F. U bar F is the one that is actually coming from the finite-element method. Okay, so what are the news? What are the new things comparing what it was a while ago? The new thing is this component here. Nothing else. And this new component is coming from the finite-element method. And it is describing deformation, displacement. So it's like basically, if you think about cantilever beam, and when you're imposing force, the cantilever beam, the displacement is like how much each of the given point of the cantilever beam has moved. So this is going to be vector U bar F. U bar F, you know that this kind of the deformation you can describe, or you can compute using the finite-element method. All right, here comes something very important. You know, what we did in a case of rigid bodies, we took each of the particles into account by using these volume integrals. So we integrated over the volume of the body, and that's the way we were able to take the entire particles. I mean, all these infinite number of particles into account. When we are discussing about rigid bodies, that's no longer possible because there is a, first of all, infinite number of particles. an infinite number of motion possibilities for each of the particles. And this is not going to be computationally possible any longer. What we need to do is that we need to limit ourselves to a certain number of motions, so the certain number of the ways that the deformation can take into place. We still can take each of the particles into account, but the way they can deform need to be limited, simply because we don't have a computational resources to make that or take that into account. That's the reason behind. Okay, so that's what we're gonna do. And again, it goes like this. Here is the equation of motion that is used in a multi-body system dynamics. And look at what we have here. So we have these generalized coordinates which describe the Lorentz reference translation and rotation, and Lagrange multipliers that takes the constraints into account. So this is going to be our vector on unknowns. This is going to be supplemented by the finite element method, and in the finite element method we wanted to learn this vector. So we wanted to solve this vector as a function of time. That's what we wanted to do. How that sounds? Big picture is pretty clear, isn't it? There's one big problem here, which we're going to revisit later, if not today, then a little later during the course. And this big problem is this: the typical size of finite element model is enormous. It is not unusual that the size of the finite element model describing the one single body consists of a 10,000 degrees of freedom, 100,000 degrees of freedom, 1 million degrees of freedom. So it means that the vector u bar f is very big, consists of a very large number of components. And this is making things complicated because, here the reference motion, which is the kind of the dominating aspect here, is described by using 6 variables. 6 variables that are used here for rigid body reference motion versus, as for example, 100,000. They don't match. The one is way too big versus another. And which one is very big is going to be, of course, this one. And we need to do something for that. What we need to do something for that is called modal reduction. And modal reduction is a concept that takes you to a concept of vibrations. And we need to conduct an eigenvalue analysis for the finite element model. And finite element, this eigenvalue analysis will tell us what are the properties of the structure. It's not telling us much, nothing actually, about the actual displacement. It's telling us the relation between the stiffness and mass. And this is an information that we can use to reduce the size of the problem. And it's not unusual that 100,000 will go down to 10. Of course, there is a price we need to pay. And the price we need to pay is that accuracy is not as great as it was with 100,000 degrees of freedom. But it's surprising that, technique, this modal reduction technique, accuracy is compromised only a very little. So it's something that in engineering applications we can live fine without going, even when we go down to the 10 degrees of freedom. This is going to take place by using this modal reduction method, and we're going to learn to use it with help of eigenvalue analysis. And eigenvalue is more about the structural properties, relation between stiffness and mass. Okay, any comments, questions so far? How things appears to be? So is it making sense, or none of this stuff makes any sense?
It feels like we look at the same equations in different classes, all everything.
This is good.
But I feel like that's pedagogical.
It is. This is the whole purpose. So you learn this thing about in Jussi Sopanen's class, and then in Marko Matikanen's class. So do you guys have a feeling that you are not making any progress whatsoever? Because moving from one class to another, same equation comes again and again and again and again. Which is great. It's still great. I know that you guys are, okay, why this is such a big deal? But once you understand the nature of this technology, everything is going to be easier after that. So one more time, is USYS class,
And then control system.
control system.
Yeah.
Control system, what course is this? Machine Dynamics. But what is another course? This is something that I'm not familiar with. Is this one that...
Control, there's this eigenvalue analysis to find the stability into it.
Right, but is it for rigid bodies or flexible bodies? I think it is for rigid bodies.
I think so, yeah.
So it's a rigid body. So it's a little different story, but again, a little bit same story too. Okay, how this all comes together. Hopefully it's going to be something that you feel super strong after you have heard about these stories. What you see is explaining is more or less the same. He is moving from one space to another, because moving here to 100,000 degrees of freedom to 10 degrees of freedom is moving from one space to another space. So this is a space mapping. Uses, by the way, middle name is a space mapping, you know that. So he's very, very good in that. So he uses space mapping Sopanen. So he's mapping from one space to another all the time. Here we don't do that much of a mapping, but a little bit too. Okay, so here's a few examples about the floating frame reference formulation that I haven't shown you earlier. These are the early developments we made. This is a three-dimensional crankshaft. And you see that the connection rod is a flexible body, just the testing purposes. So when this was when we were about to look at how was this floating frame reference formulation in details, this kind of not symbol, but this kind of exercises were used. And this is another system where there's a telescope joint, which is even today is a little difficult to model using this technology for the reason that we're going to get back a little later. But you see that it looks pretty realistic, so it's not too much off. Okay, deformation, U. How you can describe this U bar? It was called U bar F. For sake of simplicity, we're going to start calling this as a U. All the time, this U is going to be with respect to reference coordinate system that takes this large translation and rotation into account. But from this on, we're going to make a visit to look how the deformation can be described. And we are making no comments whatsoever regarding whether or not this coordinate that is going to be described, or where the deformation is going to be described with respect to, is it moving or not? So that's what's going to happen. And we're going to look at the method that is this finite element method, extensively used. And the finite element method is very general, and it can apply to multiple different engineering areas. Here we're going to use a displacement-based finite element method. Displacement-based means that unknowns will be displacement. There are other methods. You know, you can use this in a fluid analysis. You can even have a different kind of versions of finite element method where the unknowns are, for example, stresses and displacement. This is called mixed finite element method, where you're mixing the quantities, making them to be unknowns. And this is one of the techniques that you can get a little better approximation about two things simultaneously. But now we're going to look something where there's displacement based that is focused on U. How much or how well we can describe deformation. Okay, so method is pretty simple. So it's something that you take your structure, you divide your structure to something that is called elements. And these elements are connected to points that are called nodes. Now, more you have elements, the better solution you have. As a nature of the method is approximate method. So typically when you have a low number, and I'm speaking unclear matter because I say low, not specifically saying what's low and what's high. When you have a low number of elements, your solution is typically not great. It's getting better and better and better once you're increasing the number of elements. This is something that is called convergency. Convergency rate. If you, for example, have even a simple structure like cantilever beam. This is a little too simple, but let's say that you have a cantilever beam that is loaded like this way. And then you need to take a look like, how is the displacement of this end here? When you keep on modeling this by using number of elements, what's going to happen to you is that if this is an analytical solution, the correct solution, once you increase in the number of elements, this is a elements, your solution getting better and better and better. Something that is like convergency. So typically, more you have an element, better solution you have. How rapidly you get this good solution is called convergency rate. It depends on how you're selecting your elements. It can be very low. It can be like you really need a lot of elements like this. Sometimes the convergency can be actually not coming from the stiff side, I mean soft side, but it can be like this, which could be a little bit of a problem too. But this is called convergency. But the nature of finite element method is an approximate method. And it's okay solution. I mean, okay answers if you do it properly and if you have a proper number of elements. But if only. And it's good to think that, good to have a like clear criticism against the method because it is an approximate method. Okay, so these are the questions. So again, the slides will be available in a Moodle database, so no need to copy that. So we're going to take a look at about polynomials. Polynomials because, like we discussed, we can take each of the particles in the flexible bodies into account. How we do that using finite element method, that's going to be based on polynomials. And then what is related to polynomials is the Pascal's triangle. What's the deal with the Pascal's triangle? And convergency rate, we'll look already a little bit, like how fast you can get a solution that you're happy with. All right, now let's get started. So let's get started from the very simple element. Simple element that is a spring element. Spring element is something that consists of two nodes, 2 points that are both ends of the spring element. By the way, these nodes can be located in a place where you're combining one element to another, but they can be also connected or they can be also located inside of the element. Like it's very well possible that there's one node here in the middle. Or let's say that there could be 3 nodes in the middle. This is possible too. All right, so this element is something that this one node here, U1, can move back and forth to x-axis direction. Nothing but the motion like this. Here's another node and the same kind of degrees of freedom. So they consist, each of these points consist of 1 degree of freedom. Meaning that is a one way only that they can move. They can move here or they can move negatively, which is another direction. Okay. So now comes something extremely important. We wanted to learn how is a behavior between these nodes. This is what is the nature of the finite element method. We really wanted to know how is each of the particles, and there is again many, infinite numbers to be more specific, how they are moving between these 2 extremes, nodal points. That's what the finite element method is about. All right, so what we can do that? So we can approximate these pretty much any way we want. And there are many ways to do that, but the most common way to do that is using polynomials. Okay, polynomial is the way that we can describe how is the internal life between these nodes. And let me emphasize again, finite element method is all about how is the life between these nodes. That's what we're interested in. And that's going to give us that feature of each of the components that will be later used to compute the displacement that are like stiffness matrix, mass matrix, so on and so forth. How is the life between? Okay, so now it's going to be pretty simple. So we have one node here, another node here. So we have a total of 2 degrees of freedom system. 2 degrees of freedom system. Okay? So the way we can approximate this using polynomial will be this. You know, this is a continuous function that is a function of x, this guy here. And this continuous function consists of two components. And these two components are A0 and A1. And A1 is multiplied by x here. Now, how things would be different if I would add one more node here in the middle, this node here. So it would be 3 nodes. So it would be 3 degrees of freedom element. What should I do to describe an element like that? I should add one more component, and this one more component will be A2, correct? Multiplied by polynomial, what comes next is x power 2. Okay. Now, this is describing a soul of my element. This is what I really am interested in. This is like inner beauty. And inner beauty we are very much interested in. We do need this outer beauty, which is these nodal points here. But the more important here is how it looks inside. What we're going to do next is that we're going to replace these unknowns, which is A1, A0, A1. Well, let's leave this away because we're going to focus on this one here by nodal degrees of freedom. We could use this A's as an unknown and solve the responses based on the A's. But then the problem is that they don't have a clear physical interpretation. And this is, by the way, the problem of many of the other than polynomials. Yes, you can solve the displacement, but the interpretation, not so clear. So it's not clear at all. Okay, how we can make things to happen? Well, maybe we can make a use of the information we have here so we know how the nodes are located. And maybe we can use this information to create something that the polynomial unknowns are replaced by nodal degrees of freedom. Okay, goes like this. So I'm going to express this polynomial by using two vectors. The one that is polynomial coefficients, another one is my unknowns. Again, let me emphasize that you could go with this. You can take these A's and go all the way to stiffness matrix and solve this problem by using this kind of the unknowns. But again, they have no clear physical interpretation. So that's why it makes sense to do a certain level of manipulation here in the beginning, in a kinematic level. All right, what we know. So we do know that the first node is located in a place where the x is equal to 0. How do I know that? I do know because when I look at this x coordinate system, it starts here. So it's located in a place that x is equal to 0. So how it's going to look if I substitute that information to my polynomial? It's going to, if it's originally written like this, and if you substitute 0 here, this component will disappear. What is left is this on. All right? Then I will do the same, but this time x is equal to L, because I know that the next node is located in a position of L with respect to origin of the coordinate system x. All right, so this is going to be my substitution. So what if I'm going to express this similarly than this one using using the matrix notation. So U1, U2 can be expressed by using these unknowns, A's, and then something that is a matrix that we're very much interested in. Now, only thing left here is to solve this one and substitute that back to here. And then we're going to have, again, understanding how is each of the particles between these nodes, how they are behaving. To make that happen, I need to invert this one, which is a 2 by 2 matrix. Let me tell you a horror story. When I was a postdoctoral student in the University of Illinois at Chicago, in UIC, one of the first things that was my responsibility was to create the shape function matrix, the same thing that I'm doing here for the element that consists a total of 48 degrees of freedom. I'm never going to forget about the number 48. So instead of 2 degrees of freedom, so now we have 2 degrees of freedom, it was actually 48 degrees of freedom. So what that means? It means that this matrix here wasn't 2 by 2, but 48 times 48. So it's much bigger than that. So seemingly simple approach to do, because already back then, when I was younger, still young, but younger, I had this access to symbolic math tools. So I was able to use the symbolic math tools to create this, and more importantly, invert it, because otherwise inverting this by using pen and paper, inverting matrix 48 times 48, no go. No human can do that. Maybe somebody can do it, but it would be you need to devote the lifetime to do it once. All right, so the element was something that was not willing to cooperate. So every time that I made this 48 times 48 matrix, and I said to my symbolic math tool that go ahead and invert it, it says singular. Singular, singular, singular. Honestly, I spent 3 months in my life. I went to my office, I was typing this system, inverted, singular. Singular, 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 day in, day out, week in, week out, month in, month out, same story all the time, and even automated. And I tried like different kind of combination of polynomials. Nothing helped. I was very desperate, very desperate. And then one of the day, I was making a combination that I thought that's never going to work out. It was able to invert it. And this is one of the papers that is still even today is one of the most cited papers that I have ever made. It was about the elements made for multi-body application, plate elements, very high degrees of freedom. So I'm never going to forget how to do this save function. All right, so you don't need to struggle to do anything like that. Once I do the math, once I do the substitution, I'm going to get the 2 components. I'm going to get the vector of 2 components, and these 2 components are continuous functions. Continuous functions that are telling me how is it that each particles are moving if I'm going to make a move of one of these nodal degrees of freedom. So this is what is a soul of finite element method. So let's look at this again. So I have here node 1 and node 2. And if I move node 1, these save functions, I keep the node 2 where it is. These save functions are telling me how is every single particle between these points, how is it they moving? And this is what the finite element method is all about. I understand that it's hard to understand this concept because we're speaking about the element that is can only move back and forth in this nodal location. But if you move this one here, like that much, how is the particles that used to located like here, how is it they moving with respect to each other? And the motion is linear. You see there is linear behavior. But not necessarily. This linearity comes through the fact that now the polynomial that I used was very simple. And this becomes to be more clear when we look at this in a beam application, because in the beams, we have more degrees of freedom. But now this is the soul of finite element method. If not knowing how is each of the particles traveling between these points, I would have no chance to use this in a proper way. Now, I say polynomials is most commonly used to create these safe functions, which is correct. But not necessarily. There are, some people are not happy with the polynomials. There is even technology that is somewhat in a fashion, at least was somewhat in a fashion a while ago, called isogeometric analysis. And isogeometric analysis, instead of using polynomials, they use NURBS, non-uniform rational B sign. And this is something that instead of using polynomials, they use this. Why? Well, there's a clear reason. Because one of the things that in real use of finite element method takes most of the time is meshing. Meshing means that you have a geometry and you wanted to divide this geometry to elements. And of course, each of the commercial finite element method, they have the automated way to make things to happen. But usually you need to do this several times because there may be certain details that the meshing tool is getting confused. You're not able to make a proper meshing, so you need to go back and forth with your finite element that CAD software, and this takes usually more time than anything else. And now when you look at back, how is the CAD software? How the CAD software describe the different geometries, they are based on NURBS, non-uniform rational B-splines. And now if you use a NURBS in your finite element method, then this matching, or is there conversion from geometry to finite element mesh becomes to be more straightforward. And you can save time in the meshing phase. Other than that, everything works like no difference. So this is something that is called isogeometric analysis. Okay, so what next? Yes, sir.
We now have like a system with 2 degrees of freedom. If we have like a system with 48, we get like 48 of this diagrams, right?
Yes.
Okay.
Okay. Hey, by the way, can you guys do me a favor? Call me Aki, because when you call me professor, I say, okay, where the heck? So where this guy is located? So I have a hard time to recognize my name, because usually everyone call me Aki, except my doctoral students. They don't call me Aki, but they call me Aki. Come here right now. And I don't know what. I think it is me too, but I don't know why they do that. Right?
No, we call you Big Boss.
Okay, all right. Okay, anyways, because we're here in the same team. There was something else I wanted to say. Okay. Yeah, so if, this element, this particular element, here, even this one here, you can make that 48 degrees of freedom, because if you're going to do it in a way that you have here 48 nodes, so this becomes to be 48 times 48. Not necessarily making that much of a sense. And there are, by the way, in the finite element method, something that is good you to be aware of too, is there are 2 different refinement methods. Like the one that I explained here. I said that you can get better and better solution if you increase in the number of elements, which is correct. But you can also make it another way around. So you can also increase the decrease within the one single element. So it's meaning that, now we use these linear polynomials. So instead of using linear polynomials, we can use more advanced polynomials and increase in the complexity of one single element. And these are called like different names. They are called P and H refinement. P and H refinement. So if you look at the finite element literature, you can get the better solution in 2 alternative ways. Increase in the number of elements, or increase in the decrease within one element. Same story, more or less the same story. Both comes with a computational burdening. So they both requires more computational power. So it doesn't really matter how you do it, because it's going to increase the number of computation anyways. But B and H refinement, that's what it is called. Okay, so I was here. Look at this. So 4 nodes. So if it is 4 nodes, how is going to be the polynomial? Because, how is it you can select the polynomial if you have a configuration like shown here? So it's going to be 1, 2, 3, 4 nodes. Each of the nodes has a 1 degree of freedom. So go ahead and log yourself into the Socrates and enter the answer. And now the one that was saying that I'm unable to log in should be able to log in now. So the one that was communicating with the big boy, big muscle, Mustafa. Because now if you call me big boss, I need to call you big muscles too. So it's going to be, this is a 2-way road. You know that. Okay, so which one is correct? One only is correct. One only can work in this configuration. Okay, which one works? Okay, while you do that, sorry guys, I know I didn't notice that it's already this late, so it's 11:10. Soon it's going to be 11:10. So we're going to continue to discuss a little bit about this, and then we're going to look at the beam element, and then we're going to have a break, and then my presentation. Okay, let me explain you something more here. This Pascal triangle that I mentioned in one of the questions is a triangle that you can select these polynomials. So that's what it is. So it's a triangular shape. It can be a tetrahedron too if it is a 3-dimensional space. But in 2-dimensional space is a triangle. And triangle work like this. So this is telling you how is that you can select the polynomials. Okay, now we are here in a one dimension only. So we, in a Pascal's triangle, we're using one line only. So we're moving like back and forth in this direction. So this is how we're selecting the polynomial components. Typical way to select the polynomial components is that you select this one, and you actually have to do it. If not selecting this one, element is unable to describe large translation and rotation without introducing strains. And this is going to be, physically incorrect. So you have to select that. This is a minimum component that you must have with you. Second one here, if you have if you have a line, so you have to have the x2, because otherwise element is unable to express constant strain. And constant strain is something that is another important feature, because even when you have like shear distribution that is a very, very complex form, you can always look at that in a small pieces that are constant. And this is another requirement to make the element to be something that is converging correct solution. But then comes something surprising. Often these polynomials are selecting, okay, the next one is this, and so on and so forth. But some of the well-performing elements, you don't do the selection like this, but you skipping some of them. That was, by the way, the story with the one that I was able to finally find the safe functions, the one that was based on 48 times 48. So it wasn't that I was selecting everything here, because that would be easy thing to do. But it was like each one of them, and then this one, and this one, and then all of a sudden it works. And all of a sudden it's performing better than anything else. And this is something that we're going to discuss a little later. So it's conforming and non-conforming elements. The selection, like making everything in a line, is very obvious choice, but not necessarily getting the most efficient elements. Okay, now I'm going to get back to this Socrates momentarily, but let's look at how we can describe the element then. Okay, this is something that I don't think that is very important here to understand in details. But what I wanted to do is that I wanted to express the equilibrium in a sense that I have here external applied forces and then the stress that I'm integrating over the boundaries of the element. This is a little hard or complicated way to express the whole thing. But what I wanted to have here is a strain. This is strain here, strain vector. And I wanted to know how the displacement and strain are related. This is what I need to know to be able to create my stiffness matrix. The one that is here in the middle is going to be matrix or scalar of elastic coefficient. Here is my strain vector again. Strain vector, in this case, can be get if you know your displacement, and this is something that relates to displacement and strain. This is typically called in finite element literature, it is called as a B, as a kinematic matrix. Kinematic matrix that relates displacement and strain. So if there's this amount of displacement, what that means in terms of strain. All right, here relation is this. I'm differentiating this vector u with respect to x. It's going to give me strain. And the strain, when I substitute this safe function, another decrease of freedom here, this is the way that relates my strain and displacement. This is the one that is called kinematic matrix, doing this relation to me. Okay, so why this is important? Because now if I have the displacement here, it tells me how is the strain, and the strain, again, is something that I must know in order to be able to express my stiffness matrix. I went a little fast here. I don't know if you guys have a little hard time to understand this, but the true nature of the finite element method is this kinematics. How you do this relation between the displacement and strain, this is very case dependent. And I would say that is less important than understanding the true nature that is based on polynomials. Okay. Now, when I do this computing, so when I have this kinematic matrix and everything, once I finally compute everything and once I do the integration, this is what's going to be left, and this, what is going to be left, is called stiffness matrix. Now in a static finite element method, what I do is that I have my stiffness matrix multiplied by displacement is going to be equal than externally applied forces. In a finite element problems, what we do here is that we're solving this one. We're solving displacement by inverting stiffness matrix and multiplying forces by inverted stiffness matrix. Then you know the displacement, but displacement will be expressed by, well, in terms of nodal degrees of freedom. But with help of shape functions, we actually know how is each of the particles moving with respect, within the boundaries of the elements. Okay, we get back to this a little later, so we're going to look at this one more time. And then one thing that is mentioned here is that, these forces will be expressed in terms of nodal degrees of freedom, because your unknowns are this. So if you have a case that you have a nodes here, and the force is applying here, place where there is no node, you need to share these forces to nodal degrees of freedom. And that you can make it happen, again, with help of shape functions. Something that is less important here to understand, but one of the keys, or one of the kind of like a minor things that is still very important to understand, like how you actually can make use of finite element models. All right, so this is finally what you can get. So you solving this one, which is a displacement. Let's look something. I know for some reason I'm reluctant to have a break. I don't know why. Maybe because I'm not sure how well is my ERC presentation, or yeah, but I think I need to do that. Okay, so what do you guys say? Let's have a break, and then after break, 5 minutes, my presentation, and then we continue with this subject matter, but completely different story. And it becomes to be interesting because now we're going to take a look at the beam element. Beam element is more easy to understand because we're using beam element, and we look at the displacement in a transverse direction, here up and down, and then the angle here. What kind of polynomials can be used to describe this kind of the beam elements? Here, the answer is clear because it consists of 4 degrees of freedom, because 2 degrees of freedom in this node, another 2 degrees of freedom in this node. So the polynomial that will be describing the midline, this one, will be a polynomial with the 4 unknowns. Must be 4 unknowns. Okay, how much you need? 5. See you then in 5 minutes. This one and this one. And I think I'm back. Can you double check? Okay. I'm gonna be blocking these part of the slides, but I'm not gonna change the settings here. So let's put the timing on. So 5 minutes. 5 minutes is my presentation. Aki Mikkola, LUT University. I'm helping people to understand dynamics. And here I'm introducing the topic that is related to high-strength steel and how we can make a better use of the high-strength steel by tackling the problem that they are suffering very severely. And this problem is called fatigue. You know that there is a big desire to change the heavy machinery to be lightweight machinery. And you can make it happen by using high-strength steel more extensively. Big problem in high-strength steel is that elastic modulus is going to be the same as it is for conventional steel. That means that if you are able to make structures to be more lightweight, they're gonna handle the or they can handle the same amount of loading, but the deformation becomes to be bigger. And when the deformation becomes to be bigger, dynamic is something that is going to be more severe than it will be for structures that are made from conventional steel. Very often, these high-strength steel and conventional steel too, when you look at how different components are put together, they are put together by using welding. And when you're welding two components together, you are always suffering from the severe problem called fatigue. And fatigue comes for the several reasons. First of all, because of the welding process that is very severe process, it's going to introduce the high residual stresses roughly at the location that the crack can start growing. And due to the welding process, the welding itself will introduce a lot of things that are not ideal, that are serving as an initial crack. Those two things make these structures to be very vulnerable for fatigue. You can do the fatigue prediction if you know its material that is being made, which is steel in this time, geometry, and the loading. And it's most difficult to know the loading that these structures are experiencing during the lifetime of the machine. The way that I'm going to solve the problem is that I'm going to build a multi-body model that consists of these components that you can see in this slide. So there are components that are based on mechanical parts, actuators, control system, and even the user. User can be taken into account by making this to be real-time models where you actually are operating by using the real human, and the real humans are using these models. The working process depends what you want it to do, but in the heavy machinery, it could be the working process could be the ones that you're moving the dirt to one location to another. Technically, each of these points will be described by using this kind of real-time simulation model, and the real-time simulation model consists of actuator modeling, it consists of control system, and it consists of floating frame reference formulation. The floating frame reference formulation allows you to get the stress histories that are critical information in terms of the fatigue damage, and you get this in multiple different locations of the structure. Now, what we're going to do is that we're going to make a use of the floating frame reference formulation, and we can introduce it in a way that it can be used in a real-time simulation model, or even more better, it can be used in a technique that is called reality-driven simulation. Reality-driven simulation is something that we are no longer using the real-time simulation platforms, but we are taking the real machines that we're monitoring the sensor signal from the real machine. Using the sensor signals, we can force simulation model to replicate what happens in reality. And this is a kind of the virtual strain gauge that tells us what are the stresses and strains at any given time. And this allows us to make it like a mileage gauge, where the mileage getting from the new machine is very high, and it's getting lower and lower depending on how the machine is being operated. I'm the optimal person to make this to happen because I've been in the field already more than 30 years. This is a television show that was broadcasting almost close to 30 years ago. This is me telling about the same subject matter. And you see that my mileage in my face is very high, but I've been doing nothing but this thing in my entire career. Okay, that's it. My first practice. I see there's 4 minutes and 40 seconds.
Yes.
Okay. Okay, thank you. We go this every week. What are the things that I need to improve? Yes, sir.
No sound in the videos.
Yeah, yeah.
It's really annoying when there's video sound in the background
Yes.
when you're talking. It's
Yes.
really hard to understand.
Yes. Okay, I need to make a note to myself. Okay, I'm going to use this one. So the videos cannot have a background noise. Yeah, I realized that too. But this was the first time that I practiced, and it makes sense to me to practice. Also, this one, I don't think that my voice shouldn't be there. Should not be there. My face can be there, but no voice. Okay. So the voice needs to be taken away from each of the slides. What else? Voice away from slides. What else?
Maybe, I think on your first slide, the motivation slide, there you have like the
Sure.
trained. You could include this with other pictures because you talked about like welding steel together.
Yes.
Problems that comes from welding. Maybe you can put a picture from a weld and the strength
Yes.
or the softness of the steel.
And look at this. Look at this. This is something that you can expect a person in elementary school to put in there, right? You know, to draw this. So this is not professional, for sure. So and this is not clear. Even the deformation, I said that the deformation here is bigger than is here, but can you really see that? No, you cannot. So I was thinking that I'm going to replace this by animation. That there is an animation that there is a cantilever beam side by side. Another one is deformed more significantly than another. I think that would be better. Okay? This second slide is no good. But you said something else, that I was speaking about this welding thing, but never really highlighted that there is something welded here. That was never mentioned. You seems to collect all the points. What else? What else? Yes, sir.
I'm not sure, but is the title correct in the upper right corner?
Yeah.
So in the first slide, I noticed that there is a misspell.
Mm,
Dynamics here, or?
yeah, this is that what they created automatically. So it's not necessarily something that need to mean something, but they just make operation automatically. This is what this system, this proposal is called. Good point. Good point.
Is it not should be the sign of wood on each slide?
Each slide. So you want to take it away.
No,
you-
no, to put it on each slide.
Each slide.
Yeah,
Okay.
in one spot so it can be
Each slide.
and
LUT logo to each slide.
yeah.
Okay. Good.
It's against Scott's advice.
I think it is pretty good because it doesn't make that much. We still make this.
So may I give the comments as well?
Yeah.
The first slide is super empty.
This one.
Yeah, like if you want to, and also like
Yeah.
it lack the elements of hooking your audience.
Yep. So the second slide is no good.
Personal preference, I would prefer like to start a presentation with a question, so that you
Okay.
can grab my attention.
All right. Question.
Yeah,
All right.
like why should I listen to you? Why should I give you my full attention?
Question in the beginning.
Yeah, like this question you can just ask the question by yourself.
Okay.
Like you don't need to write it.
Okay.
But-
What? Yeah. Go ahead.
But like for the first slide and for the element of seeking the attention, it's super empty. Like
Yep. I agree. What about Team Finland? Any proposal? Yes.
Was this for EU project or what is it?
No. This is something that is called ERC, which is a European level funding.
Okay. Will there be like professionals in this field or are they just like team project managers or?
No, they will be professors, but not in my field.
Okay.
There will be professors, but maybe one or two could be in the field of solid mechanics. But solid mechanics is very broad area. It's very, very broad area. So panel it altogether is like 20 members. Many of them are like fluid dynamics stuff that has nothing whatsoever to do with this. So they are completely out from this field. Okay, but now I know like roughly how much I can put into my presentation because now this 5 minutes, yeah.
and also like for the starting point, and because that was also my question that like whether everybody is they're from your field.
No,
or
no,
not.
they're not. They're
So
not.
For somebody who is not from the field of designing heavy machinery, I don't know anything about it. Or
Yeah,
why
okay.
you should make this structure lighter.
Yeah, okay. All right. Anything else?
What about slides? Like a little bit later slides? Next one. It's like
This was problematic.
previous one. Yeah, it's like on the top one there is duplicated the previous slide information.
Yeah.
of this picture.
Yeah, and here, did you guys notice? I guess that what you wanted to say that this idea was to explain, how is each of these boxes are described mathematically, but they never have a time to explain these equations. So these equations are for no use at all. So I need to do something for that. I recognize that if I wanted to explain this, it's going to take more than 5 minutes to explain each of these equations. But it was an advice that there need to be equations because they want to see plot. They want to see plot. They want to see violent. And the violent thing in our discipline is equations. And the plot is the equations. But I'm not sure if I use that because here's the problem, like as you pointed out. No, they're equations, but what the heck? And then also the thing is that, I'm a little afraid that if I started to explain each of these components, it's going to take, instead of 5 minutes, it's going to take 5 hours. And they're going to be not willing to give any money to me at all.
Maybe to add a description into the site, just to each component.
Yeah.
like a word.
Yeah, something like that. Something like that. But I need to,
Mind map like structure, so that we like connect each or what equation fits what.
yeah, that's the one that I need. I think that I need that this is exactly what I need. I need to put okay, mechanics, this equation, hydraulics, one equation each, not more than that, no more than that. And then I can just say that, okay, this is based on this method, this method, this method, and this method. I'm not going to go any deeper than that because obviously the 5 minutes is not enough. Okay, here's the funny thing. This interview is going to be 25 minutes in total. Something else.
No, I'll take it afterwards.
Okay, but you have an opportunity to give a next round of improvements, not next week, but week after that. So we're going to go over and over again. Hopefully I'm getting started my lectures by this. And then if we're going to win, of course, this is going to be a good thing, great thing, which we're all going to celebrate. What was that I wanted to say?
You haven't concluded the Socrates.
Yeah, I haven't concluded the Socrates, but that wasn't in my mind. It was something else, something other than that. This one. Okay, how is the success rate here? So we got the 56 answers, which is good number. Is it going to be 100%? Okay, 100% or not? I'm thinking it is. Not exactly, but very close to it. Very, very close to it. Very close to it. Yeah, not bad at all. Not bad. Okay, here's my lecture. So let's go back to this one. And again, I wanted to focus on the kinematics. I need to do this. Sorry, guys, that I need to do this one more time. You guys also you can say that you don't want to participate if you feel uncomfortable about this my ERC business, but it's a big deal because this level of ERCs in LUT has no winners so far. So I'm pretty convinced that I would like to be the first one.
What is the ERC?
It's like European Research Council.
European Research Council.
Yes.
So if you get this, you get the funding for something, or is it like
Yes. So it's like 2.5 million in the stake. So that's what it is. And not just that, is more than a money, is a reputation, because this is extremely hard to get. So only the professors that are thinking too much about their performance applies, like me. If you think like that, you're average, don't even bother, because the competition is so severe. But I think it's highly about my performance, and that's why I even applied. But usually, it's not that many applications, and each of the applicants are very capable, very capable. So it's hard to get it. But we'll see. We'll see. More than a half will be declined after interviews. So it's still uphill still continues. All right. Okay. And now another element. Altogether another element, which is a beam element. And like I say, now this is more clear because now we're looking at the displacement in this transverse direction. And we're going to describe the displacement in the transverse direction, this direction, as a function of longitudinal direction. So now the shape functions are more easy to understand what they actually represent. And now, to get started here, we need to, first of all, we need to define these orientation parameters, or these rotational parameters here. And we're going to simply describe this by differentiating the v, which is this transverse direction, with respect to x. So this is a simple way to get this, like how is the orientation of any given point of this element. Okay, so that's what we do. The first thing in this element is to select the polynomial. You see that I'm selecting conforming polynomials because look at this. So I have my 0, 1, 2, and 4 selected exactly in order that what the Pascal's triangle is telling me. So I don't make any shortcut. But next week I'm going to show you what it means if instead of this I'm selecting, for example, A3 is going to be x power 5, which I can do. I can do that. So it's going to, yes?
Maybe a stupid question, but I don't understand where you get the A1, A0, A2, A3, the
Whole line.
that
Whole line.
thing,
Whole line. Okay, so it comes, okay, that's a fantastic question. It comes from the fact that, the number of unknowns here need to match the unknown, or let's say they need to match the degrees of freedom of your finite element. That's where they're coming from. The only thing that really matters is a number. The number need to match. So if I, for example, have an element like this that consists of a total of 3 nodes, and each of the nodes consists of 2 degrees of freedom that are motion in a displacement in a transverse direction, and then the angle. All right. So this would have 6 degrees of freedom. So then I need to select this polynomial expansion in a way that they need to be 6 unknowns, because this A's, A0 to all the way to A5 here will be my unknowns. But the unknowns as expressed by using these A's is no good because they don't have a clear physical interpretation. So I'm converting them to be expressed in terms of nodal displacement. And the nodal displacement in this case would be, this direction here, and then this partial, my first node, and then the same for a second node, which is this one here. Now I'm running out of the space, and then it will be the same for third node. This will be my nodal unknowns. And once I express these unknowns with help of these guys, it's going to give me shape functions. And your question was like where they are coming from. So first of all, you need to select how many of them you need. Okay, that's your first choice. And this is something that you cannot actually, you have no freedom whatsoever because you need to match your degrees of freedom in your finite element. That's what it needs to be. Then it's all about how you do this selection in a Pascal's triangle. Remember this Pascal triangle? You need to select the proper number of components. Proper number of components. I'm not going to write each of these components, but if I need to select 3, I need to select first 2. The rest, I can select the way I want. Honestly, I can select the way I want. And the obvious choice would be the third one is the third in a line. But if I want to emphasize certain aspects, I might not want to get third in a line, but fourth in a line to get my third component. Good. That's what I like. So anything else that you have doubts? Is this making sense? This polynomial expansion, because this is the finite element method is all about this polynomial expansion. That's what it is. That's the core content. Rest is mechanical. This is the only place you do the selection. Rest, you have no room to make any kind of selection because you need to be based on physics. No comment, no questions anymore. No comments. Okay, all right. So I see that. I don't know how I'm able to spend this much time because we don't have that much time left. But anyways, here's my polynomial expansion, and I'm expressing these by using these polynomials and unknowns. Okay, this is what I do not know. I don't know what they are. If I know what they are, I would be able to tell how is each of the particles are moving with respect to boundaries of the element. But I don't know. I don't know what they are. And I'm not happy with this kind of the unknowns because they don't have a clear physical interpretation. So what I wanted to do, so instead of using this, I wanted to express these unknowns in terms of nodal decrease of freedom. How can I make it happen? By substituting the information that I know to this kind of the set of equations. First equation is that, okay, this equation here, when x is equal to 0, how is it going to be? So all the components, this one, and this one, will disappear. Only thing left will be a0. Then I'm differentiating this one here with respect to x, and I do the same level of substitution. When I differentiate this with respect to x, this is the only one will be left. Sorry, that is a big mess. But first of all, because I differentiated, it's going to be like parcel vx parcel x. It's going to be like this. It's going to be a1 plus, is this 2x, and then it's there a2, and then it's going to be 3a3x power 2, like this. And if you substitute x is equal to 0, this is going to disappear, this is going to disappear. Only thing left is this guy. All right? Then the next one, L. I'm going to substitute L as an x. This is the first equation that I'm going to get. Second one, which is differentiated, it's going to be this one. Now I'm expressing this in terms of this famous matrix. Here is my nodal degrees of freedom. Here's my matrix coefficients, and this is my polynomial unknowns. And now I'm going to solve this one to be able to substitute this information here. Sorry, that is a big mess, but hopefully you're still able to follow me. Okay, I'm not able to, I converted this by using symbolic math tool. So this is how it looks. And now I'm going to do this substitution here. Look what I'm going to get. I'm going to get the continuous representation, what happens within the element, or within the boundaries of the element. Okay? What I'm going to get is I'm going to get 4 safe functions. And these safe functions are orthogonal in nature. Orthogonal means that they are not dependent on each other. And you can tell that when I plot them, because you see that, the second nodal degrees of freedom is angle. You see the angle here is 0. You see the displacement here is 0, as its angle here is 0. So the only one on 0 is the motion in transverse direction. Second one is representing when you are having like moment here. You see that displacement here is 0, displacement here is 0, and angle here is 0. You see that this is how they behave. And what really matters here, now you have a continuous representation, how is each of the particle, how they are represented within the boundaries of the element. That's what we need to know. This is what is key information for the element technology. All right? And the same, which is symmetric, but another nodal degrees of freedom. Here's a displacement in the y direction. This one is 0, this one is 0, displacement is 0. And this is rotation, but in another end, so they are symmetrical. Okay, all right. Now, here's a relation, how is that I can build a relation between the strain and stresses. This is something that I need to explain in detail to you, how I did this thing. It's going to be next week. But basically, I need to look at like midline here. I need to be able to tell how is something like curve that is perpendicular with respect to midline at any given time. That's what I need to know. And once I be able to express that, then I know how much the one particle here, which is off from the midline, has deformed. That's what I need to know. And this is going to tell me the relation between the strain and nodal displacement. And again, it's going to be something that is called kinematic matrix. I know that this is all coming too fast, but we're going to take a look at this next week, and then we're going to wrap up the whole thing, because then you know the basics of finite-element method. And this is pretty much what you need to know about finite-element method. So if you understand this level of details about beginning of the finite-element method, or let's say not beginning, but this polynomial expansion, you're very strong. You're very strong in the method. more stronger, that you will be able to use a commercial finance element software and able to click this and that. That's telling not much about what is the method about, what the method is about. All right, so this is it. Now, as promised, I will get back to the details next week. Oh, next week, by the way, it's going to be visiting lecture like we discussed earlier. So it's going to be inconvenient, but next week I need to be someplace else. So next week is going to be biomechanics, and then we're coming back to the flexible multibody dynamics. Okay, guys, next up will be lunch. How that sounds?
Sounds good.
All right, see you in 2 weeks.
Also about the presentation, one point about the thinking study, maybe when you present like 2 or 3 points, you can use your hands like more clearly, like first point.
Oh yeah. This is what we learned from another guy, that it's important to use hands.
Yeah.
It's important. Also, next time you need to touch my appearance. Seriously, because it's important too. Like because it's supposed to be like standing like this and like this. You need to be confident,
I was confident. I had an eye on this and it was clear.
but need to be like super confident. And any advices, I appreciate that, and I think it is good. Like point 1, point 2, point 3.
3 things.
Yeah, but we have 5, so we're stronger than him. Okay, thanks guys.